On the last article in the LT16 packet, with the aim at the top that says, "How are storms driven by climate change?" Now, I'm not gonna model what to highlight, and I'm not gonna pause and make the comments like I have been doing because you guys should be very familiar with the expectations of this. So go ahead and pause when you need to, when you're writing your annotations, and then just play when you're ready to go on. Paragraph 1. Until fairly recently, most scientists denied that global climate change and hurricane activity were related in any way. They said that hurricanes were subject to a separate cycle of oceanic and atmospheric activity that seemed to shift every 25 years or so. However, an increased body of evidence now shows that hurricane intensity, a measure of strength, is directly linked to rising global temperatures. A hurricane begins when winds blowing across the surface of warm ocean water converge to form clusters of strong thunderstorms known as tropical disturbances. The heat of the water provides the energy that these storms need to build. As they do, water evaporates from the ocean surface and enters the air as water vapor. As the vapor rises and cools, it condenses and forms clouds, a process that releases heat. The heat warms the center or the eye of the storm, which in turn causes more water to evaporate. Meteorologists call this cycle a heat engine. As long as a storm has access to warm ocean water, this engine will continue to drive the storm's growth. Since 1970, climate scientists have noticed a gradual warming of the world's oceans. Most attribute this warming to an increase in greenhouse gas concentration in the atmosphere. In trying to determine whether there's a definitive link between rising sea surface temperature, SST, and hurricane intensity, scientists have noted that a 0.5 degrees Celsius rise in global SST between 1970 and 2005 resulted in a 4% increase in atmospheric water vapor. Again, water vapor is associated with producing larger and more powerful hurricanes, so there may be a connection. The Saffir-Simpson hurricane scale is used to classify hurricanes according to their intensity level. In order to be classified as a Category 1 hurricane, a tropical cyclone must have a maximum sustained winds of at least 119 kilometers, which is 74 miles per hour. The highest classification on the scale, Category 5, is reserved for storms with winds exceeding 249 kilometers or 155 miles per hour. The classifications are intended primarily for use in measuring the potential damage and flooding a hurricane will cause upon landfall. Scientists are under a lot of pressure to accurately predict hurricane direction and intensity. As Hurricane Katrina, a Category 4 storm that inundated New Orleans and nearby coastal areas in 2005 demonstrated, lives and property are at risk. While scientists have gotten pretty good at predicting the direction of a hurricane, they are not as good at predicting the intensity. This is largely because they lack the tools that enable them to read all of the changes in terrain and water temperature that might cause a hurricane to strengthen or weaken. Using satellites equipped with weather radar, they are beginning to better visualize the internal structure of hurricanes. This may enable them to detect signs that a hurricane is about to enter an intensification phase, which can aid the hurricane preparedness. Climate change is adding to the cost and threat of hurricanes. While there have been extreme storms in the past, recent history reflects the growing expense of hurricanes. 4 of the 10 costliest hurricanes on record in the United States occurred between 2017 and 2018. Hurricane Katrina in 2005 remains the most expensive hurricane on record, costing $168 billion. In 2017, the hurricane season was historic, with hurricanes Harvey, Maria, and Irma costing nearly $300 billion together. It's important to note that while stronger hurricanes are more damaging, there's nearly 50 million homes and at least $1.4 trillion in assets within an eighth of a mile of the coast, and a growing amount of property is at risk at coastal areas. An important driver of the increased cost of hurricanes is increasing development in coastal areas. U.S. coastal populations grew by nearly 35 million people between 1970 and 2010. As more development occurs in harm's way, regardless of climate change, the more likely damage will grow. In addition to damages to buildings, hurricanes threaten infrastructure, undermining energy systems, water and sewer systems, transportation, and flood management structures. Stronger hurricanes pose a significant risk to public health and human lives. Hurricane Katrina caused over 1,800 deaths, and Hurricane Maria in 2018 caused 2,981 deaths, mostly in Puerto Rico. Disruptions to water supplies and power systems can cause risk for waterborne illness, environmental contaminants, mosquito-borne illness, and cause hospitals to close or affect care for patients. Conditions left in the wake of a flooding disaster, when sanitation is compromised, displaced people are crowded together, and there's an abundance of standing water, and diseases flourish. Cholera is probably the best known example, made possible by poor sanitation, in particular when a source of drinking water is contaminated by disease harboring human waste. So do mosquito-borne viruses. Flooding inevitably means a lot of standing, unsanitary water, the perfect breeding grounds for mosquitoes. Malaria outbreaks in particular have repeatedly occurred after floods.